Okay, I'm going to be talking about this new tool in the search for extraterrestrial intelligence. It's called Optical SETI. I learned about this working on a small project at Princeton several years ago, and I decided to bring it to your attention since it's a new technique, and I think it's still relatively unknown, and it's going to be quite important in the future, I believe. Now, I'm not an expert on the subject. I played a pretty small role in this project. The true experts, of course, are the groups at Berkeley, Harvard, and of course the SETI Institute right here in town. Okay? Now, you guys are all familiar probably with radio SETI. In the simplest form, radio SETI is the equivalent of just taking an antenna, pointing at some interesting target object, then take a very sensitive receiver and very carefully tune the receiver, essentially listening for like a Morse code signal or something like that. You're looking for a very narrow spectral line. Okay? That was first proposed in 1959, and measurements have been going on ever since. Okay? Now, 1 year later, Towns, one of the pioneers of lasers, proposed you could use light just as effectively, and that was largely ignored. Okay? So there's been very little work done on that. Okay? Now, there is a version of optical SETI which is very similar to radio SETI. Okay, where you take a telescope, you point it at a nearby star or some object where you're looking for intelligent life. You have a spectrometer, which is looking for a very narrow spectral line. So this would be something like someone shining a laser at you, flashing on and off. Okay, and there is ongoing work in this area, and that's not what I'm going to be talking about today. I'm going to be talking about something completely different, and I was rather amazed when I first learned about this material in this little project I'm going to tell you about. Okay, so here, the idea of optical SETI is very simple. You take the biggest, most powerful laser you can find. And we're not talking about something on top of a bench. We're talking about something like the National Ignition Facility a few miles outside of town here. This thing can put out 500 terawatts of power, but it only can do it for a very short time, for about a nanosecond. Okay, so you build one of these things, okay? It puts out this incredibly short pulse of this high-intensity radiation. Then you take it, and you put it backwards through a Keck telescope. What's that telescope do for you? It concentrates it into a very narrow beam, and you aim this at some star nearby where you think there might be a nice planet orbiting where you want to communicate. Okay, so this telescope, since it's a nice narrow beam, it doesn't get spread out, so it's still going to be pretty intense when you get there. Now, what happens when you're there? If you're on that planet looking back at the Earth, during that 1 nanosecond that laser is on, that laser outshines the total intensity of that star by a factor of 10,000. And that's independent of the distance between us and the star. Okay? You don't have to know exactly what frequency the laser was at. That one narrow line is brighter than the entire optical spectrum of the star, which means you can use a very simple, inexpensive detector, and you're just measuring the total intensity of light coming from that star. And if that thing blips up by a factor of 10,000, you detected the signal. Now, what else is important is the fact that there is no known astrophysical process that can do this. So this is sort of a signature of somebody trying to send you something. Okay? Furthermore, if you're within, say, 100 light years of the transmitter, you use a very tiny telescope, something like a 1-meter telescope, like we have had on the campus of Princeton University, and it's a very inexpensive detector, costing several $1,000s. So here you can do this wonderful experiment where you can transmit over these interstellar distances and receive, and you don't have to do this searching for the exact wavelength. Okay. Now, the question is, are we going to transmit or are we going to receive? Well, let's see. To transmit, we have to build an ignition facility, a few $1 billion, a few $100 million for a telescope, and we'll transmit. And by the way, it's going to be a delayed gratification, because we're going to send something 20 years later, the signal's going to get there. Hopefully, someone there will detect it, and maybe they have a big setup like this, and they can talk back to us. Signal comes back, it's 40 years later, and maybe your grandkids are eligible for the breakthrough prize. Okay? Okay, so of course, we're going to be smart. We're going to receive. Okay? So we're going to just get this little telescope, this 1-meter telescope. There's a spare one on campus. We see this pulse coming into the sky. Boom. We're famous. We get the breakthrough prize right away. Okay? Now, you might ask, why in the world would anybody bother transmitting? It's going to cost a ridiculous amount of money. Now we're going to pull in Moore's law. Okay, this is the little magic. Of course, nowadays it costs us $1 billion to build one of these things. Okay, but maybe in 100 or 1,000 years, Sheldon Cooper in his garage can do this. Right? So why don't we assume that we're not at the beginning? There are civilizations a little bit more advanced than us, and they'll do the transmitting for us. Okay. So that's exactly what the assumption is. So Harvard went on and actually built one of these systems to receive this radiation, okay? And so they had like a 61-inch telescope, and one of the key things they did in their detector is it has to be very high-speed detectors in order to detect this very, very narrow 1 nanosecond pulse. It's a billionth of a second long. And these things occasionally have these false detections. Okay, what they do is they will report a photon arise, some light arise when it doesn't. So what they do is they split their light into 2 beams and run half of the light into each detector, and they only consider valid detections when both detectors go off at the same time. Okay? And the chances of both of them having one of these random events at the same time is very rare. So that reduces their number of false detections. So they began observing in 1998, and they were looking at about 1,000 nearby stars, and once a night they would get one of these signals that passed all their tests. Now the signal did not repeat from the same star from night to night, okay, and they couldn't find any patterns, but they couldn't be absolutely sure it wasn't coming from there. So how are they going to solve this problem, figure out what's going on? So the key is, of course, build a second one of these instruments and have that also look at the same star. And that's where we come into the picture, okay? Okay, so now Dave T. Wilkinson heard about this, and you may have heard of this guy. I think there's a satellite named after him, okay? So he got some volunteers together, okay, and that's where I come in. I was one of the volunteers working with him. It was faculty and staff of the university and some local amateur astronomers. Okay, he found an alumnus to fund the hardware. Of course, you know, there's very little funding for SETI. Okay, and we all got together working weekends and evenings and refurbished an unused 36-inch telescope on campus. We were working with Harvard, so we cloned their instrument. We began simultaneous observations with them. So we would look at the exact same star at the same time. Okay, and the idea is if they saw something, we should also see something, but we wouldn't see it exactly at the same time because the light, since we're at different locations, the light's going to have to travel slightly different distances to get to us. And we can use that as a cross-check, that we get the signals at just the right amount of delay, and then that's a really good sign that they're actually coming from the sky rather than some instrumental effect. Okay? So we did this. We began observing in 2001. We had about 2,000 simultaneous observations. About 1,000 different objects. Okay? And at the end of this whole time, we had one candidate event which seemed to pass all our tests. Unfortunately for us, about a week before that event, we had a nasty thunderstorm which came, and it knocked out our GPS system, so we didn't have the accurate time measurements. Okay, so we couldn't verify that the time delay between the measurements was accurate enough to confirm that it was on the sky. So we went back and re-observed that spot several times, but unfortunately it never reoccurred, so we had to toss out that result. We could not confirm it. Okay, so this was published in 2004. Okay, and that was one of the last papers I believe Dave Wilkinson was on, actually. Now, more recently, Harvard continued on, and they found a new detector which would look for these nanosecond pulses, but it could look at 1,000 spots at the sky at once. Okay, 1,000 spots. So they decided to make a survey of the entire sky that was visible from the Harvard area. So they built an instrument using a 72-inch mirror, okay, and they were basically just scanning the entire sky. It would take them about 200 nights to cover the whole sky, and this is an ongoing effort. This was funded by the Planetary Society, and it's still going on today. Okay, and of course, they haven't had a positive detection, or you would have heard about it. Okay. Meanwhile, Berkeley sort of improved on that first detector that Harvard used. One that had the 2 detectors for coincidence, but it was coming up with about 1 false detection per night, if you recall. Okay, well, they went and improved it and put 3 detectors. They took the light, split it 3 ways, and they were able to reduce the false detection rate down to about once per year. Okay, so they have that system operating. Okay, so what's going to happen in the future here? Okay, well, of course, our goal is to detect ET, but of course, we don't know if that's going to happen tomorrow, 10 years, 1,000 years from now. So a real reasonable goal, I think, would be more to maximize the probability of detecting an ET in the next few years. Okay, so how are we going to do that? Well, these optical methods are largely unexplored. We're sort of surprised to find that even that small effort that I mentioned between Princeton and Harvard, which was basically a dozen people and $50,000, was considered significant enough to show up in a lot of the papers I was reading preparing for this talk. Okay, so you can see that the level of effort going into this is largely unexplored. Okay, we're always looking for new ideas, and I'll talk about one or two of those in a minute or two. But the whole idea is we've got to get in and start getting observing data. We've got to just start getting data because there's no chance of seeing a signal without data. The large observing effects only started relatively recently. I told you, originally this idea of optical SETI was ignored. Okay, it was only in about 1998 that large-scale observations began. There's very little observing time compared to radio SETI, and so they really have to make up for lost time. Okay, so if you're going to observe, you need instruments. So there are two ways we can get more instruments. We could just make more of what we've got, or we can try a new instrument. Okay? Well, if we want to do more of what we got, what we do is we can just take some, say, the original instrument we did, where we looked at one star at a time. There are quite a few underutilized 1-meter telescopes. It ends up being that a lot of these 1-meter telescopes are in areas that got built up, where now the sky is bright and the seeing is terrible. It ends up being for these observations, you don't really need good seeing, which means it's okay if the atmosphere is bouncing around or there's background light, because you're only looking for the change in the intensity. Okay, so we were observing from Princeton, which is not known, I'll tell you, for dark skies. Okay? And hopefully they could do that, use that new Berkeley detector that only has, say, one false detection a year. Maybe we could do these by funding it sort of like the Princeton model, where you get some donor to sort of fund some of the hardware you need, and then you do all the manpower with volunteers. Okay. The other thing you could do maybe is build out the, clone the Harvard design where they were surveying the whole sky. It would cost a little bit more money. Okay, it would be nice to get one of those in the southern hemisphere because they can't see parts of the southern sky from there, and just take more data like that. Now, there's one issue going on with these two experiments. Unfortunately, both of them in any instant are only looking at a very, very small fraction of the sky. Okay, and that's a bad thing. Now, they told, for example, that Harvard instrument, I told you it takes them 200 nights to cover the sky that they can see. But over that 200 nights, typically they're looking at any given spot for 1 minute. Okay, now that's not a very good thing. So, the guy at the other end is sending these radio signals to you, and you have to be on the right star at the exact right time, that 1 minute when that signal happens to be arriving. So the odds are not very good at all. Okay? So really what you want, your goal should be to observe the entire sky all the time. Okay? Well, you could try to build a lot of those instruments, but it would take 200,000 of those things in order to cover the sky the whole time. So that's totally impractical. Okay? So, that's just not the way to do it. So there simply right now is not the technology that exists to cover the entire sky looking for these short nanosecond pulses. Okay, so what are we going to do about that? Okay, well, the other thing these two first experiments have in common is the fact that they are only the first searching for signals that we know how to build today. The numbers I gave you for this National Ignition Facility laser, okay, who says that, why can't we apply Moore's law once more? Maybe these transmitters are better than that. Maybe instead of making nanosecond pulses, they can make microsecond pulses. Or maybe they can make millisecond pulses. Okay? Why not look for those also? We can just use Moore's law one more time and be optimistic. Okay? And that's what exactly this next project is about. And I just learned about this recently while preparing for this talk, and I thought it was quite exciting. It's a new program run by the SETI Institute. It's called Laser SETI, and their goal is to look at the entire sky the entire time, 100% of the time, but looking for these millisecond pulses now. So they're quite a bit longer, 1 million times longer than the first ones, but nobody's ever looked for these before. Okay? So they can do this with a very simple instrument. They basically take a standard CCD detector, that's charged coupled device that amateur astronomers use. And that is basically very similar to the detector that's in your cell phone camera or a digital camera. Okay, it just picks up the light. They take a standard camera lens to focus the light from the sky onto that. And they put a diffraction grating, which is something that splits the light into these different spectral colors. Okay, so they can also get the spectrum of the light that's coming in. Okay, and they use the CCD, this detector, in a very non-standard way. Normally, you take an image and you expose it, and then you read it out and get the fixed image. They're doing a continuous readout, which actually smears the image in one direction. Now, they sort of lose the spatial information in one direction. What it lets them do, though, is get time information. They can see they can detect them, and a pulse lasts only for a millisecond. And that's a very clever, non-standard way they're doing it, but it's very nice. And in addition, detecting the pulse, they get the spectrum of each pulse, so they can tell whether it's coming from a laser or some more natural physical phenomenon. Their design goal was to have one false detection every 10,000 years. That's the way they were designed for the technology. They haven't verified that yet, but they're trying to, you know. And obviously, they don't have to achieve anything nearly that good in order to have a very good instrument. One of the limitations of this, though, is they can only detect quite bright pulses. So these transmitters have to be very nearby because they're using such a small lens to collect light from the sky. Okay? And the interesting thing is, though, these millisecond pulses that they're looking for would have been rejected by these previous instruments. Those previous instruments were looking for just nanosecond pulses. And if they saw anything as long as a millisecond, they would have rejected it, saying there's something wrong, there's a fault in the instrument. Okay, so it's sort of interesting that they would have been rejected like that. Okay, so they've built the prototype of this thing. There's a picture of it on the left of the camera. Each camera can observe about a 24th of the sky at a given time. So they package 4 of those together, which means they can observe a 1/6 of the sky. And on the right, the diagram there, it shows red dots are where they propose putting these around the world. They get 24-hour coverage of the sky, full coverage of the sky, of course. So they need a total of 6 observatories for full sky coverage. Actually, you'd want more because obviously any point can be weathered out or something like that, or a fault. Plus, if you have more, it's possible that the object will be picked up by 2 of those cameras. And if it's picked up by 2 of those cameras, that's a really good thing, because then you can use that same trick about the time delay to verify the signal really came from the sky. Okay, so this thing is funded through an Indiegogo campaign. They have funded the prototype camera, and that's what they're verifying now. And if that works, then they're going to try to raise some more money and do this worldwide deployment. Okay, it's a very, very nice program. A little bit further in the future, there is this new detector which actually is related to some of the things we were using in the microwave background. And I just heard a talk on this a few weeks ago at Princeton. It had this big long name. We just call these things M-kids. Okay? It's a new kind of detector that detects individual photons. Okay? And the ones we have here actually have an array of 20,000 pixels in a rectangular grid. Okay? So it is looking at 20,000 spots simultaneously, and for each one, it will measure the time of arrival of the pulse within a microsecond accuracy. Okay, it can tell you which pixel it landed on. Plus, it gives you the energy of each photon coming on. And essentially, this has 0 dark noise. It has no false counts. If a signal comes in there, you know a photon came in and hit it. Okay, so these are being developed at Santa Barbara. On the right there is a picture of 2 of the little pixels. Those are the little tiny things that light comes in, and there's a whole array of 20,000 of those. Unfortunately, this is a candidate for a new instrument that would now detect microsecond pulses. So this would be a sort of an instrument maybe that would go between the nanosecond range and the millisecond range to try to pick up that intermediate range. Unfortunately, these only operate at these very low temperatures, like Lyman Page mentioned earlier. It's the same technology that's used in some of the microwave background experiments at 1/10 of a degree above absolute 0. So they're quite expensive to operate at now. So for SETI, it's probably in a few years in the future, but it is a possible candidate technology. So what's going to happen? We somehow get these things going, we get all this data coming in. What do we do with the data? Okay? Well, of course, you have to remember, in science, you never prove anything true, as we all know, right? You falsify things. You say something is wrong. And so what we have to work is then you have to eliminate alternate explanations for the data. Okay, so our hypothesis we're working on is we want to say it comes from extraterrestrial source intelligence, but of course we have to eliminate all the other possibilities first. Okay, so one of the first things we want to do is establish the origin of the signal. The question is it an instrumental artifact or some interference, or is it coming from the sky? So, I mean, that's a pretty straightforward thing to do. Your question is whether if it's always coming from the same spot when you observe the sky, that's a pretty good sign. If you take the instrument and point it away and go back and it shows up again, that's a pretty good signal from the sky. But again, the best one probably is having 2 instruments see the same signal with the proper time delay. Okay? So now once you've established that the signal is coming from the sky, then the question is it the signal of a natural astrophysical explanation, or is there something more than that? Okay? So how are you going to do that? Well, you're going to take everything you know, everything from your detector, and try to sort of model the data, but that rarely will be enough to determine something like that. So the first thing you're going to do is you're going to get help by telling other people what you're seeing, and you want the guys with the gamma ray telescopes and X-ray telescopes and infrared stuff all to look there, right? Because you want as much data as you can to try to make a model of that object, okay? Now in this process, you may actually end up getting some help from the transmitter. Remember, the whole concept here is that somebody is trying to talk to you, so he's trying to make that signal look obvious to you, okay? So for example, one thing they could do is say the signals arrive in little bunches. Okay, and the first bunch has 2 pulses, the next bunch has 3, then they have 5, then 7, then 11. Those are just prime numbers in order. It would be very, very hard to have some natural astrophysical process that knew about prime numbers and could do that. So they may be able to tag something, put some sort of little tell in there, okay, that would help us identify this, eliminate the possibility that this is coming from a natural astrophysical source, okay? So in the very end here, what might we learn from this stuff? Well, say we do all this stuff and we don't get any signals we don't expect. Is that a wash? Of course not, right? In science, we realize that a negative detection isn't no information. It lets us set limits. We know what parameters we use to make the measurements, so we might set limits on the intensity, the frequency of occurrence of either the millisecond, nanosecond, or microsecond pulses, depending on which instrument we're talking about. And that limit can also be used to limit future astrophysical models. Say somebody comes up with a model where some pulsar flashes occasionally, it has a very bright flash, and if we happen to have this limit data on the books, we can rule out that model right away, okay? What if we get unexpected sky signals? Well, in the past few decades, we've really become increasingly aware of the existence of a wide range of transient events, like gamma ray bursts. We saw pulsing neutrinos when supernova of 1987A went off. More recently, there are these fast radio bursts. And of course, we saw the gravitational wave transient signals from LIGO recently. Okay? So the ability to detect these new optical transients on the nanosecond, microsecond, millisecond timescales may really reveal previously unknown astrophysical events, which would be very exciting in its own right. Okay? Of course, if we're very, very lucky, they'll detect a class of events that can't be explained with any reasonable astrophysical sources. And if we conclude that they're likely from an extraterrestrial civilization, I think that would rank above one of the most important discoveries in all of history. Thank you.
We have time for some quick questions. Yeah, right there in the center.
Thank you. One of the important things about detecting these signals is narrowing the bandwidth to increase your signal-to-noise ratio. And in your circumstance, you have a spatial, you have temporal, and you have wavelength. Okay, so the question is, there are a couple of ways of narrowing it that I did not hear you talking about. One is spatial, because we know which star systems have planets that are likely to be habitable. So I would focus on those. Okay. I assume you've thought about that.
Yes.
The other part of this has to do with wavelength. That is, the periodic chart doesn't change as you move around the universe. So the materials and essentially typically ions that produce very high intensity, typically near infrared pulses are very well defined. So if I was sitting out there in the universe trying to shoot a cheap high power laser at somebody, I'd pick like neodymium or a ruby or something like that. In particular, one that has a window in typical atmospheres, and I would look at that particular wavelength. So that would also basically help you. Doesn't solve the temporal problem, but it solves the spatial and the wavelength problem. But you didn't talk about either of those simplifications.
Well, the point is, right, what I was speaking about, this is the first round of things. You're absolutely correct with everything you said. So basically, this detection will work with things within 100 light years of us right now, okay? Because basically that ratio, that 10,000 to 1 brightness ratio, without knowing the wavelength, is independent of distance. However, in order for it to be bright enough to use this very low-cost detector that I was talking about, okay, it has to be very close to us. Now, what you're talking about, if we started applying those techniques, you're right. And what that would do is that would let us look at things much further away, okay? So you're absolutely correct, but again, this is That means you have to start putting spectrometers, for example, on your system and things, which are expensive in general. So you're absolutely correct, but given the funding situation for SETI, this is a starting place. But you're absolutely right.
We have time for one more question, right here.
Thanks for a beautiful talk. You pointed out these two wonderful detectors. The original one was photomultiplier tubes, and then you talked about the CCDs, which are millisecond,
right,
and the new thing, the MKIDs, which are microsecond. I just wanted to point out, maybe you know about these, but maybe the rest of the audience, there's a new kind of detector, silicon photomultiplier tube, avalanche photodiode arrays, that are...
The discrete amplification type?
Yeah, so
yes,
right.
Yes.
So these things are sensitive to nanosecond, millisecond, up to second time scales, microsecond. And we are planning an array. They're very cheap because they're used in medical imaging. Yes. So they're $3 each. So we're buying 100,000 of them. We're planning to put them behind a big geodesic dome. Maybe you know about this with Berkeley and Harvard and UC San Diego. It's another one of these all-sky things, but we can be sensitive to lots of different time scales, including the nanosecond time scale.
Oh, fantastic. I apologize for not including, I did not run across that in the literature while I was preparing this, but it's wonderful to know. Thank you.
There's one more question there in the back.
Thank you for your talk. What happens if you actually find somebody? What are you going to do? What if the signal's convincing? What are you going to do?
Well, I believe actually the SETI Institute has a program now to come up with a scale for the verifiability of one of these signals. But the point is, my belief is when one of these signals is detected, it will not be a secret. Remember, the first thing I said is once you see a signal and you're trying to figure out an astrophysical source, you go out and you ask other people to make measurements on that thing to get all the data you can. And once that information goes out, there's so many people involved. So for example, there are two sort of interesting results going on. You've heard about this Tabby star thing, where this star that's dimming very, very, like 20 or 30% over short time scales, right? And there's this wonderful result from the Breakthrough Listen Challenge, where they have this fast radio burster that went off like 15 times in a few hours. And both those are public knowledge because they want other people to look at them. So it won't be the question for what are we going to do. I guess it's the question is what's society going to do. But so it's not like one group is going to have the answer and sort of keep it secret. I think just the nature of this kind of experiment means that this information will be public. And one example of this, the LIGO results recently for the neutron-star merger, there were rumors all over the place before that paper actually came out because of this exact fact that the LIGO triggers sent off messages to universities, instruments all over the world where they were trying to look simultaneously for the various other signatures of the neutron star burst. And there are so many people involved that it's just impossible to keep security when you have these hundreds and hundreds of people doing these measurements.
Okay, let's thank all the speakers from session 2.